Hello, this is IMechE speaking, and I'm going to set the scene with some introductory remarks about the basics of centrifugal compressors. Dr. Hamid Hasbi will continue with part 2 afterwards, giving more detail about the design of inducers. This list gives you an idea of the topics that I will be talking about. I'm going to go through some background, a little bit about energy transfer, the key non-dimensional parameters in compressors, some information about performance maps, how to design the inlet, how to design the outlet, and some important aspects about the design of the diffuser. This shows some pictures of particular applications. These are probably the most important applications for compressors. The top left, we have a single stage compressor. Here it's called a blower. You can see the impeller and you can see diffuser vanes around it. On the top right, we have a radial compressor joined to a turbine in a marine diesel turbocharger. And both of these types of machine can go up to a pressure ratio of about 10. But if you need to go to a higher pressure ratio, you have to have multi-stage compressors. Bottom right is a picture of a two-stage helicopter engine, again with open impellers so you can see the blades. And this would probably be a pressure ratio of up to 12. Note that all of these three pictures that I've talked about, you can see the impellers quite clearly because they're open with a clearance gap between the blades and the casing. And they all look remarkably similar. And that's one of the things that I want to show you. On the bottom left, we have a multi-stage compressor. Here you can't see the blades because in this case, each of the impellers has a shroud cover on it. If you look carefully, you'll see that each of the impellers get narrower as you go along the shaft towards the right. And that's because as the pressure ratio of the machine increases, this requires narrow impellers. This is a typical very, very high pressure application for process gases. The sketch on the next slide shows on the left an axial compressor rotor. The flow comes in axially and leaves axially. And next to it, there are three sketches of different types of centrifugal impellers. There is a diagonal impeller where the flow is a mixed flow going partly radial and partly axial. Then there's a radial impeller with an axial inlet and a radial outlet, and a purely radial impeller where the flow is radial at inlet and at outlet. The centrifugals have the advantage over the axial stage that because the centrifugal force is in play when the flow moves radially, they can get to a pressure ratio about 3 times that of an axial stage. The next slide shows typical cross-sections of two types of impeller. The first cross-section on the left is a single-stage impeller where you can see it has an inlet guide vane in the axial inlet. It has an impeller with no casing on it, no shroud on it, and it has a diffuser coming into a volute. On the right is a typical multi-stage impeller used for an multi-stage inline compressor. This has an inlet guide vane in the radial inlet. It has an impeller with a shroud cover attached to it. It then has a diffuser, but the flow has to come back to the next stage, so we then have what's called a crossover channel and a return channel down to the inlet of the next stage. And because the flow after the diffuser still has swirl in the flow, there are blades in the return channel. The energy transfer in a typical impeller is best described in terms of the velocity triangles. If you look at the notation on the left, the inlet to the impeller is 1, the outlet of the impeller is 2, and the outlet of the diffuser is number 3. And the velocity triangles at these conditions are given on the right. At the bottom, the number 1 shows that there's practically axial flow coming into the inlet impeller of the impeller. The blade is going round at a blade speed here given as u1 at the inlet, and those two velocities combined give the relative velocity at the inlet, which has a certain direction, and the designer chooses the blade angle at the inlet to match that direction. Now moving to the impeller outlet, position 2, the flow through the impeller has a drop in relative velocity, so W1 is bigger than W2. The blade speed increases across the impeller, so U2 is much bigger than U1, and now the combination of W2 and U2 gives us an absolute flow given by C2, and this is the absolute flow going into the diffuser, and the diffuser of course is designed to catch that flow, so the inlet angle is matched to the flow angle there. And the diffuser decreases that velocity, C2, down to a much lower velocity, C3. This can all be plotted in a HS or Mollier diagram, where you can see the static and the total conditions at those three conditions. And what's important to see is that the impeller produces a pressure rise from P1 to P2, but at the same time produces a very large kinetic energy at the impeller outlet. Roughly 55% of the pressure rise is produced by the impeller, and the diffuser takes the kinetic energy at impeller outlet and slows that down to give another 45% of the pressure rise. This is also best described in terms of something called the Euler equation. The Euler equation applies to all turbomachinery and says the work done on a shaft is given by the change in the blade speed times the swirl component of the velocity. The swirl component is the velocity in the circumferential direction. This can be presented in an alternative form, written here, so you can see three different terms. The equations to do this can be found in any textbook, and both Hamid and I are just at the moment writing a textbook which will appear in 2019 by Cambridge University Press, and you'll hopefully buy one. The three terms are A, B, and C, and they're described here. A is the difference in the kinetic energy related to the absolute velocity at inlet and outlet of the impeller. This is positive because the outlet velocity is much higher than the inlet velocity. The second term, B, is the decrease in kinetic energy across the impeller, and because the outlet kinetic energy W2 is less than W1, this term is also positive. And the third term is called the centrifugal effect. This is the pressure rise that arises due to the fact that the impeller is going faster at the outlet with a higher blade speed U2 than it has at the inlet U1. Now this last term doesn't exist for axial compressors. The blade speed at inlet is the same as the blade speed at outlet, and that's the reason why axial compressors can't make such a high pressure rise. The key non-dimensional parameters that we use to define the performance of radial compressors are listed here. A flow coefficient, it's a non-dimensional form of the volume flow. A work coefficient, it's the non-dimensional form of the enthalpy rise, made non-dimensional with the tip speed squared. And a tip speed Mach number, which is the blade speed divided by the speed of sound at the inlet to the impeller. Starting with the work coefficient, a typical value would be 0.65. This means that if you know the blade speed, you can calculate the enthalpy rise across the machine simply by multiplying this value of 0.65 by the blade speed squared. And the pressure rise equation is given below, the last equation, and a plot of that is given on the bottom right. The tip speed Mach number is along the horizontal axis, and the pressure ratio is on the vertical axis. And you can see that with a tip speed Mach number of 1, you get a pressure ratio of 2, and with 1.5, you get about 4, and so on. So the main effect that causes a pressure ratio in a centrifugal compressor is the tip speed Mach number. If you want more pressure rise, the wheel has to rotate faster. A typical wheel for a small turbocharger might have a pressure ratio of 2, and it has a tip speed Mach number of 1, which means the tip speed is 340 meters per second. Now, this means we know the tip speed. Finally, we try and find the diameter. Now, if you plot the efficiency of many different stages against the flow coefficient of those stages, as I've done in the top right-hand diagram, you find that there's sort of a general trend that somewhere in the middle, with a flow coefficient of about 0.09, there's a sweet spot where you get good efficiency. If you have a flow coefficient which is much too big, the efficiency drops, or if you have a flow coefficient that is too small, the efficiency drops. So using the equation that's now for the flow coefficient and saying we've got a flow coefficient of 0.09, if we know the volume flow, we already know the tip speed, so now we can find the size of the machine. So just these two equations provide us quite a lot of information already. We know how fast it's got to go, and we know its size. So if we know the outlet diameter, the next question is, what's the inlet diameter? And here's a sketch of three impellers, all with the same outlet diameter, but with different inlet diameters. Starting at the left, if I have a small inlet diameter, the axial throw coming into the wheel has got to go very fast. And because it's at a low radius, the inlet has a low blade speed. So we get a certain relative velocity. Going to the right, I've got the same diagram for an impeller with a large inlet diameter. Now the blade speed is high, but the through flow velocity is low. And to the right of this, there's a plot showing how the inlet velocity varies with the diameter. And there's conveniently a point in the middle of the choices of different inlet diameter, which gives the smallest inlet velocity. This is very good for reducing the Mach number at the inlet and for reducing all the losses, which tend to be proportional to the velocity squared. Now, this analysis can be pursued further to give the diagram on the left shown here. This shows the mass flow in a non-dimensional form against the axial inlet Mach number and how this varies for different blade angles at inlet. And the choice of the minimum inlet relative Mach number by selecting the inlet diameter always gives an angle very close to -60 degrees. So you can optimize the inlet very simply from this diagram. Depending on the relative inlet Mach number, and a value of 1 is exactly 60 degrees, you end up with impellers that have the same inlet angle. In order to reduce the velocity further in the inlet, every other blade is cut back, and so we have what are called splitter vanes. So both the choice of inlet angle and the choice of splitter vanes is what we've seen in all those other pictures, and that's why they all look alike. Now the pressure ratio is determined by the outlet. The inlet determines the flow, the outlet determines the pressure ratio. And the Euler equation, which is given here again in a different form, can be rearranged to give you an equation which is linear in the flow coefficient at impeller outlet. And here the plot on the left-hand side, on the right-hand side, shows the work coefficient for different impellers with different back sweeps. Back sweep is the difference is how much the impeller blade is leaning backwards against the direction of rotation at outlet. And as you can see, this very simple diagram agrees very well with measurements of all these different impellers. Now this diagram is very important because it shows if you have no back sweep, you get a high work coefficient, but if you have a back sweep, you get a lower work coefficient, and you get a work coefficient against flow characteristic which increases as the flow decreases. And this is very important for the stability of the stage. I can show that on the next slide. If you consider the middle diagram and we have no back sweep, we get a work coefficient of 0.9, and a variation of the flow with the work with flow is a horizontal line. If we consider we have a certain efficiency curve, we can see that the efficiency times the work, which is effectively the pressure rise, reaches a peak at the pressure rise reaches a peak at the peak efficiency. Well, this is no use to man nor beast because left of that, the flow becomes unstable. When the pressure ratio starts to drop with flow, the flow is unstable. So we tend to have a back sweep. We have a work coefficient about 0.65. This has a sloping line for the work against flow. And now when we reach the peak efficiency, we're not yet at the peak pressure rise. So the peak efficiency is away from this point where the flow becomes unstable. Going the other direction, you could have a forward swept impeller. You would get more work. You would get a higher pressure rise. But unfortunately, the stage becomes unstable before you reach the peak efficiency. So you get a very poor efficiency. An example of that is the next diagram, which shows a performance map. We've talked about the inlet. We've selected the inlet to get the right flow, and the picture here shows an impeller with back sweep. And there are two maps. One on the right-hand side is an impeller with back sweep, and here you can see the peak efficiency is right in the middle of the map, and you can operate safely away from the problem of the instability line. The instability line is called surge. Each of these different speed lines finish at the surge point where the flow becomes unstable, and they go vertical at the choke point where no more mass flow can go through the machine. So you need a wide range between these different points. This gives you a map looking like the one at the left, on the right if you have back sweep, and like the one on the right if you have no back sweep, where the peak efficiency then occurs on the surge line. This is no use to man nor beast, and so all impellers have back sweep. The only issue now remaining in the design is what sort of diffuser we can use. It's quite interesting that you could have a vaneless diffuser. You don't need vanes in the diffuser, but in that case the flow decelerates linearly as it goes radially outwards. If you put in vanes, you can have a vane diffuser, and this decelerates the flow more in the same radial space. So you can have a more compact stage, and you get a high pressure rise coefficient and a better peak efficiency. The vanes diffuser has to be designed well, taking into account any flow non-uniformities at the impeller outlet to avoid noise and vibrations. Unfortunately, vane diffusers are better in terms of efficiency, but because of the vanes, as you move to off-design operating points, they tend to have less operating range than vaneless diffusers. So finally, a summary. Radials versus axial stages. Radials have a pressure rise about 3 times that of an axial stage. They have a lower efficiency than an axial stage, and they have a lower flow compared to an axial stage. But they have wider characteristics than axial stages. The two non-dimensional parameters that are really important are the flow coefficient, and I would recommend a value of 0.09, and the work coefficient, I'd recommend a value of 0.65. The design of the inducer inlet determines the flow, and nearly all impellers will have an inlet angle of -60 degrees at the inlet, and to reduce the flow blockage at the inlet, they will be designed with splitter vanes. At the outlet, we have back sweep between -20 and -40 degrees. This gives lower work, but increases the stability, which is very important. Fortunately, it also gives higher efficiency. Unfortunately, it reduces the amount of work, so to get the same pressure rise, you have to go around faster. If you'd like to play with these ideas that I presented, PCA have a standard software which you can download onto your iPhone. It's free. It's called Vista CCD, and I wish you all the best playing with it. Thank you.
Hello everyone, and thank you for attending this talk. The fundamentals of centrifugal compressors have been discussed in the first part. In the second part, we concentrate on the design of transonic impellers by first discussing the sources of the loss and efficient design of transonic passages, and then we look at the 3D design of the impeller, mechanical considerations, and finish with closing remarks. In a transonic impeller, the inlet relative Mach number reaches supersonic levels, especially at the tip section of the blade, resulting in aerodynamic shock waves inside the passage. For a typical centrifugal impeller design, the occurrence of the shock waves becomes almost unavoidable at pressure ratios higher than 4. And the inlet relative Mach number can reach a value of 1.4 or above, depending on the design. The presence of the shock results in extra aerodynamic losses, and therefore the design of the tip section becomes critical in these impellers. Looking at the shock itself, the total pressure loss across a normal shock is proportional to m squared minus 1 to the power 3, where m is the component of the Mach number normal to the shock. For an upstream Mach number of 1.3, the static pressure across the normal shock increases by a factor of 1.8, incurring only 2% total pressure loss, as you can see in the diagram on the right-hand side. This makes the shock itself an efficient means of compression, although the losses increase strongly with increasing the Mach number. However, for Mach numbers higher than 1.3, the losses can increase so significantly due to possible boundary layer separation downstream of the shock. In general, the interaction between the shock and the boundary layer results in a sudden growth of the boundary layer thickness downstream of the shock on the suction side of the blade. The low momentum flow inside the boundary layer is pushed towards the casing by the action of the centrifugal forces, resulting in the so-called radial transport phenomena. We can see this in the change of the direction of the flow vectors across the shock in the left-hand side figure. And the resultant secondary flow moves towards the casing and increases the loss and blockage development in the tip region of the impeller, as can be seen on the figure on the right-hand side. Another source of aerodynamic loss is the interaction between the shock and the leakage flow, which can result in sudden expansion of the leakage vortex and possible vortex breakdown downstream of the shock. The resultant relative total pressure deficit originating from boundary layer and leakage flows can result in early breakdown of the flow when they interact with adverse pressure gradient inside the passage. So overall, these make the performance of transonic impellers very sensitive to the design of the tip section. As an example, here we see the performance of two impellers with different tip loading at the same mass flow. The difference in the loading is achieved by modifying the front part of the blade, while the rear parts are exactly the same for both impellers. The blade on the left with higher tip loading shows a very strong loss and blockage development near the tip compared to the blade with lower tip loading, and this has resulted in a narrower operating range and lower efficiency predictions in CFD calculations for this impeller. In general, the transonic passages can operate in two different modes. If the shock is detached from the leading edge, the flow condition is referred to as unstarted, and the shock-related losses increase due to the existence of a strong normal shock at the inlet of the passage. The shock losses can be reduced if the shock is attached to the leading edge of thin blades, resulting in an oblique shock at the inlet. It should be noted that at this condition, which is referred to as unique incidence condition, the passage is effectively choked. An example of an impeller designed to operate with unique incidence condition is shown here. At low pressure ratios, choke condition, there is an oblique shock attached to the leading edge of the main blade, and the main passage shock, if it exists, is located deep inside the passage. The shock moves upstream with increasing the back pressure. The peak efficiency is a function of shock-related losses as well as the efficiency of energy transfer to the flow downstream of the inducer, and it tends to occur just before the shock is expelled from the passage. If the shock is detached, increasing the pressure reduces the mass flow and the inlet relative velocity, but it also increases the relative flow angle at the tip, which results in a higher pre-shock Mach number due to Prandtl-Meyer expansion of the supersonic flow at the leading edge of the blade. Near the stall point, the shock is normally expelled from the passage. This comes with a number of challenges. It should be noted that in order for the inlet to operate with attached shock, the splitter choking must be avoided. In other words, the splitter should not choke first. Also, small turning in the uncovered part of the passage is needed, which could result in thicker hub section to maintain the stiffness of the blade. Also, tip section is effectively choked at the design point, which means any increase in the flow capacity has to be delivered by the inner part of the blade, which may result in higher turning and higher incidence in this area. If the Mach number is higher in the inner part of the blade, these could compromise the performance, and at the end a balance has to be achieved. Overall, the choice of the right design strategy depends on whether performance is to be maximized at a specific operating condition, or good performance levels must be achieved over a range of flow and speeds. Now we move to 3D impeller design. Regarding the impeller design, there are two general choices available. The most common approach is a ruled impeller design to allow manufacturing by flank milling. In this case, the surfaces of the blade are defined using straight lines or ruled elements, connecting point pairs between hub and shroud sections. So the angle, thickness, and lean distributions are specified only on hub and shroud sections of the blade. This results in lower manufacturing costs and lower design costs, of course, but gives less control over the geometry in the inner part of the blade. In high-speed applications where high inlet Mach numbers exist along a large part of the span, we may move to freeform impeller design, which removes the geometrical constraints from the inner part of the blade. And therefore, nonlinear angle, thickness, and lean distributions can be specified at several span-wise locations. However, the blade now needs to be manufactured by point milling, which results in higher manufacturing costs and also higher design costs. Another advantage of freeform design is that it also allows more complex 3D design concepts, such as leading edge sweep, to be easily implemented in the design. The idea behind leading edge sweep comes from the swept wing theory, where the shock strength is reduced by reducing the component of the Mach number normal to the wing. However, early attempts with backward swept axial fans showed negative impacts on performance, especially on operating range, and this was due to the presence of the end walls in turbomachinery. One major impact is the effect of the casing on the position of the shock. For the range of Mach numbers encountered in turbomachinery, the shock always turns normal to the casing near the tip. Therefore, sweeping the leading edge backward moves the shock closer to the leading edge of the blade, while sweeping the leading edge forward moves the shock further down away from the leading edge. The stall tends to happen when the shock is expelled, and therefore backward sweep tends to reduce the operating range, while forward leading edge sweep could improve the range. The effect of the casing on the tip loading is also important. It follows the fact that the normal pressure gradient close to the wall is very small, and therefore the loading of the blade at the tip is affected by the loading of the blade section just under the tip. So if we move the tip section of the blade backward, the loading at the tip increases at the leading edge due to the blade loading under the tip. And the loading decreases at the trailing edge, as there will be no blade sections directly under the tip at the trailing edge. In the same way, if the leading edge is swept forward, the loading at the tip reduces in the front part of the blade. The application of the leading edge sweep in centrifugal impellers can be further complicated because of the geometrical constraints in the radial impellers. The impeller tip width at the outlet has to remain constant, and therefore sweeping the leading edge forward and backward also changes the length of the shroud. It also changes the rake angle at the trailing edge, which can change the impeller work input and also the stress levels, and these have to be considered or corrected in the design. Conventionally, some degrees of backward sweep has been used in centrifugal impellers for mechanical reasons, but designs with forward swept impellers are gaining more attention. An example of the application of leading edge sweep and freeform blading is shown here. In general, the pressurized capacity of a compressor reduces as its flow capacity is increased, and this is demonstrated in the diagram here in terms of the conventional design space for centrifugal compressors. In the current case, the design was deliberately pushed outside of the conventional design space to explore the efficiency potential in this area of the chart. This resulted in a highly loaded transonic mixed flow impeller with an inlet relative Mach number of 1.4. The leading edge is swept forward, and the tip section is designed to operate with an attached shock at the design point, achieving an overall stage isentropic efficiency levels of above 80%. Here is another example where the performance of a free-formed high-pressure ratio impeller with an inlet relative Mach number of 1.4 again was compared with the performance of a ruled impeller designed for the same duty using the same design philosophy. It was shown here that a barrel-type forward-swept leading edge could achieve high performance levels, same as forward-swept impeller, while satisfying criteria for mechanical integrity, which were more difficult to meet using simple forward-swept impeller. Although both impellers have very similar tip sections, as you can see in the contours of relative Mach number and entropy at the tip section, the swept impeller had a weaker shock and lower entropy generation at the tip. It also had a weaker shock boundary layer interaction on the suction side of the blade, resulting in weaker radial migration of the boundary layer flow, which can be seen from the direction of the flow vectors downstream of the shock, shown by the red arrows in the figure. Overall, these resulted in higher efficiency of the swept impeller. So far, we discussed the design of the inducer to achieve high efficiency levels at a single operating point. But compressors often need to cover a set of target operating points, and a compromise between the efficiency, flow capacity, and operating range has to be achieved across the performance map. As an example, a typical compressor map used in automotive turbocharger applications is shown here. The aim is to maximize the efficiency at low speed, low flow condition point A, while passing the flow with an acceptable efficiency level at point B. A large impeller trim could easily pass the flow at point B with high efficiency, but will have a low efficiency at point A due to large inlet recirculation at the casing. From the point of maximizing the efficiency at point A, a small inlet trim and throat area is needed, but this would limit the maximum flow capacity and possibly the efficiency at point B. So at the end, a compromise between impeller trim, throat area, camber distribution at the tip, and so on should be reached to achieve acceptable performance levels at both operating conditions. With this note, I move to mechanical considerations. The mechanical integrity is generally considered in the design in terms of stress and vibration characteristics of the impeller wheel. The stress analysis is commonly done using cyclic symmetry analysis. We generally maintain a minimum disk burst margin of 1.4 in our designs at PCA, and we look at the limits on bore and vane stresses. The vane stress fields can be further complicated with the application of 3D design concepts. In general, if the blade is lean towards the pressure surface, under centrifugal load, the tip section moves towards the suction side, and this results in high tensile stress on the pressure side and high compressive stress on the suction side of the blade. If, for example, the middle of the blade is moved towards the pressure side, then in a running condition, the tip section tends to move towards the pressure side, resulting in high tensile stress on the suction side in the middle of the blade, while the midsection tends to move towards suction side, resulting in high tensile stress on the pressure side near the hull. In fact, this presents both challenge and opportunity to modify the stress in free-form blades. Regarding the vibration, it is common requirement that the impeller first flap frequency should be above 4 engine order. Regarding higher engine orders, the number of stationary vanes can be chosen in such a way to avoid interference near the design speed. But crossing cannot be avoided at all speeds. One strategy is to avoid having strong excitation forces by moving the leading edge of the diffuser further downstream. And a radius ratio of 1.15 is typical in most of our designs of PCA. If necessary, a force response analysis can be performed to determine the magnitude of the alternating stresses, although this is not a part of normal design process. Such an analysis involves prediction of the aerodynamic damping as well as aerodynamic forces. The process is described here using ANSYS software. For calculation of the aerodynamic damping, the displacements from Modal analysis calculated using ANSYS Mechanical is imported into CFX. The cyclic work is calculated using a flutter type analysis in CFX and is used to calculate the aerodynamic damping ratio, which is needed for mechanical calculation. The aerodynamic forces are calculated using transient calculations, either full transient or transient blade row methods such as time transformation. Then the components of the forces are mapped on the mechanical model, and alternating stresses are calculated using harmonic force response analysis, in this case in ANSYS Mechanical. This brings me to the closing remarks. So occurrence of aerodynamic shock waves can significantly increase the aerodynamic loss at the tip section of the impellers, and for transonic impellers, the performance can be optimized by careful design of the inducer section. The 3D design concepts can also be used to further improve the performance at high speeds. However, they may result in performance losses at operating points away from the design condition, so attention has to be paid to that. The design strategy depends on the overall requirements of the compressor, and compromises are often made to achieve acceptable performance across the operating range. Thank you very much for your attention, and I'm happy to take questions.
Paul Wallace has asked what considerations must be made as ambient temperature increases. I believe this increases the relative speed of sound. Well, firstly, we tend not to use the relative speed of sound. We always tend to be talking about absolute speed of sound. Secondly, the increase in the ambient temperature does increase the speed of sound. And because it increases the speed of sound, it reduces the tip speed Mach number. And reducing the tip speed Mach number effectively reduces the pressure ratio, because the pressure ratio is a function of the tip speed Mach number. So that's the main effect of an ambient temperature increase. The second part of your question is what considerations should be made with respect to modern manufacturing processes such as 3D printing and ALM when designing a perfect diffuser. Well, I would say, firstly, diffusers are difficult. A good diffuser needs a pretty sharp leading edge, and it needs a very accurately controlled throat area. So any way in which you can use modern manufacturing processes to improve those should give you a better diffuser. I'll go to the second question. Are there any best practice methods to reduce the noise of high-speed centrifugal compressors? No.
Mick, I can try to answer that.
Yeah, thank you.
So the noise in high-speed impellers is very much affected by the strength of the shock, and so the general approach to optimize the efficiency by reducing the strength of the shock also is beneficial in reducing the noise.
Thank you, Hamid. The next question, the next two questions, and then there's another one as well. Can we have a copy of the presentation, please? Could we have the slides? I leave that to IMechE to decide how to deal with that. Here is a question for me. For high-speed impellers, making reference to one of my papers, a method to estimate the performance map, is the map prediction still good? This is from Antonio Escamilla. There are two papers out there from PCA engineers on map prediction. One was produced by me and Chris Robinson, and that's the one he's referring to here. There is a subsequent one, which is published by ASME, and it's authored by myself and Danielle Rush, and that gives more information about the accuracy of this map prediction method for high-speed impellers. Hamid, the next question is for you. It says, do you see any significant benefits of using freeform designs for diffuser sections to reduce secondary flow losses?
I have to say, when we tried it in the past, most of the focus was on the impeller, but on the diffuser, we generally got little improvements over conventional design. So what we found is the overall parameters of the diffuser, such as area ratio, throat area, the incidence on the blade, or average incidence of the blade, was more significant than the 3D design. It doesn't mean that it cannot improve the design at all, but also the flow field at the inlet of the diffuser varies significantly across the map. So if you optimize the diffuser for a particular point, then that may result in consequences for other points across the map. So it has to be done with a lot of care.
Hamid, may I add something to that?
Of course.
I know of lots of studies where people have tried to improve the performance of diffusers by having freeform designs of the inlet, such that the inlet angle is adapted to the inlet angle of the diffuser is adapted to the outlet flow angle of the impeller. Most of these have amazingly little effect. I think mainly the reason is that at the outlet of the impeller, the channels are narrow and there's a very strong mixing taking place, and so that a freeform design is not necessarily any improvement. Those of you who know what a pipe diffuser is will understand that that is quite a complex type of diffuser, where this mixing tends to be enhanced by having a very complex leading edge of the diffuser. So there could be a benefit there. I have little experience of those. And a subsequent question here, the question, by the way, is from Gursharanjit Singh from City University. It asks, could we use freeform designs to improve diffusers in a tandem configuration by combining the diffuser and the de-swirler, which is downstream of it? Well, again, I have very little personal experience of this, but I've read a lot of publications on it, and I've never been particularly convinced that these things are any better, but they're often used in pumps, and in one of the textbooks on pumps by a man called Gulick, G-U-L-I-C-H, and the book's called Centrifugal Pumps. You will find lots of pictures and diagrams of complex freeform designs for the diffuser section, but pumps are different to our machines to a certain extent. Hamid, any more comment on that?
No, I agree with you, Mark. Generally, our experience is that freeform blading was more efficient at high-speed impellers rather than downstream components.
The next question comes from David. I don't know how I pronounce it. LEC. He's from Rolls-Royce. He asked, "Is there any techniques?" I suppose he means technology to actively control the running clearance, hence controlling the surge margin. Well, it's quite possible to use some form of thin casing which is closely spaced to the impeller, and I suspect by adjusting the temperature of that or by injecting flow onto the back of it, one could adjust its shape to control the clearance, but I don't know of any published work on that at all. Hamid?
Me too, Mick. I mean, in centrifugal compressors, the common approach is passive enhancement methods, casing treatment, and in some cases, upgradable material on the casing. I personally don't know of designs with active clearance. I'm sure people tried it before, but I have no knowledge of that.
Yeah. I've seen it in practice, but it's confidential.
Okay, fair enough.
The next question is the million-dollar question for compressors. How do we make the compressor map wider? This comes from Gavin Fowler of Jaguar Land Rover. So how can we have a better surge margin but maintain the choke margin? Well, get a design from PCA engineers is my answer. Of course, this is really difficult thing. My experience is that the range of stages is mainly affected by the Mach number. So if you want a wider range, you have to design for a lower Mach number. Of course, then you have no pressure rise, so it's a bit of an awkward thing. Essentially, what I'm saying is if you want a wider range, a two-stage machine, both of which stages are at lower Mach numbers, would have a wider range. Hamid?
Yes. As far as the single-stage compressors are concerned, I mentioned that in the presentation that a compromise has to be achieved. So if you're in a car turbocharger, if you're concerned with low speed, low flow, that really implies that you are looking at smaller trims and smaller throat areas. That obviously limits the choke flow at high speed. So then you start to compromise the design by applying more turning or more aggressive design of the tip in order to open up the throat. That has consequences in terms of efficiency, but that's one of the ways you can widen the map.
Again, from David Elise of Rolls-Royce, has there been any attempt for variable geometry? In a radial compressor, there are two different sorts of variable geometry that are often used. There can be inlet guide vanes, which are variable, or there can be variable diffuser vanes, and both have been used. The inlet guide vane is probably better because it changes the swirl coming into the impeller, and this means it can either reduce or increase the flow and the work going into the impeller. Variable diffusers are able to be used to shift the characteristic, but they have no effect on the impeller. So at low flow, you still have a high work input. This will be chapter 14 of our new book. Yeah. I'm sorry if that's not a good enough answer. Hamid, would you like to say anything about variable geometry?
I think you covered it well, Mick.
Okay, thank you.
Yeah.
Of course, there's also situations where people use variable inlet guide vanes together with variable diffusers, which gives the widest possible operating range. And if you combine that with variable speed, you've got you can put the map anywhere you want. I thank you all for listening, and I thank you very much for the interesting questions. And if you'd like more information on the questions you've asked, please drop either Hamid or me an email at PCA Engineers. Thank you very much, and have a nice day. Bye-bye.
Thank you. Bye-bye.